our main target is icequakes. That is, the ice is not like a static sheet, like a metal plate that won't budge or move. There are thermal stresses, there's wind pushing, so the ice is constantly deforming, and it can also snap. And this snapping then is what we call an icequake. That sounds familiar to earthquake. An earthquake would be meaning rock snaps. In this case, an icequake means the ice snaps, and that kind of sends out waves that we are measuring. Essentially, these devices are recording 24 hours a day. They are sampling at 500 hertz, so they make 500 measure points per second. And whatever vibrations are on the ice, in the water column beneath, even sound that would be propagating across the lake in the air is recorded by these devices. So these instruments, as you said already, they're called geophones. Geophones are, if you like, a cheap version of a seismometer. These geophones record seismic waves, so there is a mass in them that would respond to any kind of infinitesimal motion. So that means that the data that are recorded by these masses in them, that move in them, are converted into electric voltage. And these particular devices that we have been installing, they come fully equipped with a recording unit as well. It's also possible to have them internally powered, but for this experiment we connected them to external batteries, so they are able to record, let's say, up to a couple of weeks autonomously. There's no real-time data transmission, so devices like that are capable of doing that if they are equipped with a special soft and hardware. But for these campaigns, for these short campaigns that last a couple of weeks, up to months, the internal data storage is what we do, yes. One of the main goals of this study is, because we have only, let's say, 15 sensors installed, that we try to learn as much as possible from these 15 individual point recordings. And we would like to get that number further down. That is, we would like to learn as much as possible from as few devices as possible, just to get the overhead down. So the colleagues that have been initiating this, which are colleagues in Grenoble, they will be mainly responsible for the data analysis, and their main goal is, try to come up with new or improved processing techniques to learn more about these snapping phenomena that I described. And that is, first of all, not or independent of this climate change topic. When we're able to improve our processing techniques, this could be transferred perhaps also to other cryo environments, as you described. But then to connect it to the climate change topic would be to have many data points, many observations over many years at many sites to really get a, let's say, consistent or coherent picture. So first of all, the manufacturers have to deliver devices that are recording at, let's say, -20, -25 degrees for days on end. So it's a hardware issue first. The other aspect that is challenging is, of course, to have the humans getting out there and having the experiment done. So that's well out of most of us' comfort zone. But this is what many earth science related projects are about. You go to places that are typically far off main civilization hubs. So that's, it's the same thing. It's like a desert environment, but if you would go into like a sand desert or like a water desert, the oceans, it's a similarly, let's say, hostile and logistically demanding environment.